Our great, it is our great pleasure to welcome Peter here to give this keynote. Peter is a researcher at CWI and at Vrije University or Vrije Universiteit. I don't know how to pronounce that, in Amsterdam. And Peter is most well known for his work on the MonADB system. This is what we all know him from, and for that also he won the ACM Systems Award. He also received a 10-year Best Paper Award at VLDB, became a Humboldt Research Award, Humboldt Research Fellow at TU Munich. More recently, he's quite active in graph database systems, which is what we hear about today. One very short comment. These keynotes, they will be recorded because they will be played back in Block B. So be aware of this. In case you ask questions or so, you might get recorded. Okay, with that, I'd like to hand over to Peter.
Thank you very much, Jens. I am audible. That's correct. And visible. Perfect. Yeah. Very good. Okay. Well, it's of course a great honor to be here, or rather not be there. I'm at CWI currently. I have a small audience accumulated here that's listening live to me. I of course would have loved to be in Edinburgh, but alas, it was not to be. So yeah, thanks for inviting me to give this talk. The title of which is The Sorry State of Graph Database Systems. And let me just head off. So during this talk, I will be comparing graph and relational database systems quite a bit, and also provide you quite numerous pointers to related literature. So about myself. So I'm somebody who comes from the database systems side, and my PhD thesis, as was mentioned, was about one of the pioneering column stores for analytical database systems, MonADB. And I would here like to thank specifically Martin Kersten, my advisor. Regrettably, he is not in good health, and I hope he will still be able to recover. After working on MonADB with Martin, I went on to work on a system called VectorWise. That's the system introduced vectorized execution and lightweight compression techniques, which are now commonly used in analytical database technology. And so that is definitely on the relational and analytical side of relational. But later I moved into benchmarking, and specifically benchmarking of graph data systems. So I was the scientific lead of a project called LDBC. That was an EU project at the time, the short EU project, but later LDBC became an industry and academic non-profit organization around graph database benchmarking. And specifically, it developed two graph benchmarks called the social network benchmark and the graphalytics benchmark. And we'll be seeing some snippets of that during the talk. So that has kept me definitely in the graph data management community. And this LDBC, in fact, because it became a meeting point for the graph database vendors, it became also a discussion place. And one of the things that was discussed was, well, the need for a common graph query language. So we started a query language task force in LDBC that produced a research specification called G-Core. So that was done in conjunction with industry people like from Neo4j and Oracle, among others, but also with researchers from the theory community, among who Marcelo Arenas, who will also give an ICDT keynote later. And later I will also talk about how this work was influential. Namely, LDBC started collaborating with ISO, and specifically with the working group within ISO that's responsible for the SQL standard. And the upcoming SQL standard, which we expect now for 2023, will include significant graph query functionality, and that goes in the name of SQL PGQ. So in this keynote, there will be two halves. So in the first half, we'll basically talk about functionality of graph data management systems, so data models, query languages, and what systems are out there. And then in the second half, I'll go more under the hood and talk about how these systems work from the inside. First, focusing on some common mistakes in the spirit of Mike Stonebreaker. I'll call these the 6 blunders of graph system architecture. And then I will give you an overview or a blueprint of what I think is a competent architecture for graph database systems. And eventually, I will also highlight the SQL-PGQ proposed or the standard in progress. Yeah, so first about, okay, what are graph data management systems in the first place? So, so graph data management currently, I would say, has gained a foothold among practice. Certainly, it's a popular topic also in research, but also, let's say, in terms of systems out there, it is a niche. It's a growing niche. Initially, graph data systems were mostly of the RDF kind, speaking Sparkle as a query language. But in the last decade or so, most growth has been coming from property graph systems, Neo4j being the most popular one among those. If you want to know more about what people are doing with graph data systems and where graph data management is going, then I would like to recommend a recent article in CICM, The Future is Big Graphs, written by a lot of colleagues of mine, and also the 2 surveys produced by the group in Waterloo on use case scenarios, techniques, and challenges in graph processing. So these 2 references I've put in there. To summarize, I think that graph data management systems are very popular for data integration tasks, data cleaning and data enrichment tasks, but also fraud detection, lots of recommendations, recommendation generation, historical analysis, root cause analysis. And the data on which these tasks are run are, you would say, obviously, well, graph shaped. So originally, certainly knowledge graphs, but also graph shaped data such as social network data, telecommunication network data. But it's a misconception to think that graph data analytics or graph data queries are only relevant for data that's obviously a graph. It is also and increasingly popular for relational data, tabular data that you find in relational warehouses, in data lakes. Because what we are doing in a graph in that case is we are investigating the connection patterns of how tuples join with each other effectively. And this is, so anywhere where you have a join, you can also analyze the connection patterns in that join with graph techniques. But also, let's say, if you do data mining and you do maybe similarity detection among entities, then you will get maybe similarities between entities. You could think of these similarities as edges forming a graph, and then you can again analyze the patterns of similarities, and that would lead you to use graph database management systems. So what does a system like that look like? Well, in this case, I will focus on the property graph data model. A system like that will support a graph query language, or at least a graph API, but most systems now also support a query language, support also some graph visualization. If we focus on the graph query language, then some building blocks that I will be describing are subgraph matching, relational queries, path queries, and stored procedures. So here is an example. Here you see an example of a property graph. So we see a person, Alice, who speaks English and French, liking artists, in this case Oasis, and being a member of a forum. I also displayed here, so what you basically have in a property graph is a directed graph where the edges and the nodes and the vertices have labels potentially. Person and tag are labels of a vertex, and likes and being a member of are labels of an edge. And these vertices and edges, they can also, these entities, they can have properties defined on them. So these are key value pairs, such as speaks English and name is Alice. These systems typically are not requiring you to define a schema up front. So it is a schema last or a loose schema. Nevertheless, I drew also a schema of this particular property graph for your reference. And in fact, one of the activities of the LDBC is in researching. So this is mostly an academic activity, but there is also strong commercial industry participation, is researching what is a graph schema, in fact, how that would actually look like. And the topics of study include constraints in property graph schemas, meaning what is a key in a graph, what is a primary key, foreign key constraint, how can we specify properties, so basically the typing and the structure of properties, and do nulls make sense in graphs, of what role would they have. And I would like to point you to a recent paper in Sigma 2021 coming out of this working group on keys in property graphs, one of the first published results. So, well, I said, I mean, most of the growth recently has been in property graphs, but the other popular data modeling in graph systems is obviously RDF. And in RDF, you have triples that connect a subject to an object via a predicate. And if we ask ourselves, what is the relationship between these two? Well, actually, these two models, they are different. They don't subsume each other. Olaf Hartig wrote a paper on how you could potentially map them. What's effectively needed if you would represent this information in RDF is that all the properties would become separate triples, which you see here, but you wouldn't be fully there, because in property graphs, the edges also can have properties. So we had likes since 2004, which is not represented yet. And you can get around that or work around that in RDF by redefining this graph and turning the edge actually into a vertex and then attaching another triple property on it. But for the moment, for the rest of the talk, I will be mostly talking about property graphs. So let's look at what property graph queries look like. First, basic graph patterns. So here we see the syntax that has been introduced by the Cipher language of Neo4j, where with kind of ASCII art, where you have arrows and connecting variables that are bound to either vertices or edges, form patterns. If the arrow doesn't have a direction, it can match either direction. So you see that in nose, it doesn't have an arrow in there. And here we ask in this query for two persons, P1 and P2, that are both member of the same forum, and we want them in. We want no duplicates, and enforce this by checking that one ID is smaller than the other ID. So in this particular example here, you would get binding. So this query returns actually a table. So you see a result table there for every row. In every row you have a column for every variable, and then it contains the bound value of that variable. So we have A, B, and D, we have A, B, and E, and B, C, and E as outcomes of this particular query. So it's interesting to observe that very often graph query languages, Cipher certainly, they query a graph, but they return a table. This is also, by the way, mostly true for Sparkle. Okay, so if we ask ourselves, can we also do this in SQL? Because I told you I would be comparing and contrasting with relational database systems. Well, you can. You could store a graph, of course, as tables, as a table of vertices and a table of edges. And here you would have two edge tables, namely one for the nose relationship and one for the member relationship. And you can express this same very query in SQL, in the SQL that you see here, and get roughly the same answer. Not entirely the same answer, but I will, because this will actually give some more answers, because you because of the binding semantics. In SQL, you get all possible bindings that match. We call that homomorphism semantics. In Cipher, you actually get isomorphic semantics, but I will not get into these details here. If we look at more complex patterns that you can express in graph query languages, then, for instance, you can think of optional matches. We depict those here with dashed lines, or negation and aggregation. So here we are asking for people that are member of a forum, and then do not know a person that that is potentially also a member of this form or not. It's an optional match, and we count those. And we see in this particular result of this, well, maybe strange query, that we also get a count of 0. And this is where the equivalence with relational data management would point you to an outer join, because otherwise a count would, of 0 would not appear. So the optional match is actually causing that you also see this count of 0. And if we look at the relational equivalent, then things get already a bit more hairy. We can definitely observe that this SQL query is longer. And we do see the appearance of the left outer join for the optional match. For the negation, you then see a subquery with a not exist clause, which internally in a database system would typically translate into an anti-join. And we see a group by and aggregation appearing in the SQL query as well. But definitely, one might already argue that indeed for usability, Cypher for these kinds of queries is better than SQL, because you have to write more SQL text. This will get worse because now we are moving on to shortest path finding. So here we see a small graph. We want to find paths. Actually, we want to find the length of the shortest path between Bob and Fleur. And this is the way you see here this match shortest path predicate that encloses a pattern, where you also see the appearance of a cleany star, nose star. That is the way to express unweighted shortest path in Cypher, and the result of this is 3. So there are in fact also 3 paths, and they all have length 3 that reach Fleur from Bob. If we would do the same thing in SQL, then we would have a person table and a nose table, and the nose table would have 2 foreign keys to the two persons connecting them, and effectively we would be looking for a chain of tuples in nose that would connect the ID 2, which is Bob, towards ID 6, which is Fleur. And if you want to write a query that computes this, then yeah, truly we get into hairy territory. I would bet that not many people would venture out to write such a SQL query, but it is possible. So what you see here is a with recursive query. So it's a recursive SQL query. Not all SQL systems support this. And a with recursive query consists of 2 parts. So it's an initial part that seeds the query and union all with a second part that joins the recursive table paths, which is being returned here, with itself. So it adds more bindings. In this particular implementation of shortest path, we also add a variable level and a variable target reached. So in the level, you see which iteration of the recursion this was generated in, and in target reached we keep whether we have found Fleur already. So when this becomes true, this is the stopping condition, and no further iterations are made. So if you take a close look, well, we won't be really trying to understand this, but you'll see this structure of, well, creating the initial edge that starts as source person Bob, and then in the union all part, you compute all the time whether you have reached the target, which is when you get to Fleur, but also have to do cycle detection to keep this more or less fast, or well, no, I wouldn't say this is fast. And yeah, so you see quite a bit of repeated code as well, because you have to test for termination, and this would not be creating this path recursive table is not all. You then again have to join this back to the person table to find the names and actually get a meaningful path out of this, or extract the path. Because if you would look at the paths table, not all paths in there actually lead to Fleur. Only the ones that finish at position 6 are the ones there are 3 of them, as we already saw, would be the paths you would be looking for. So this is definitely not for the faint-hearted, and yeah, I don't think we can call this usable from the SQL side. Then we move on, we up the ante even a bit more, and we go to weighted shortest paths, and then things really become programming contest level. And So this is a completely unreadable, complex query, maybe doable. It's like a simulation of Dijkstra's algorithm in temporary tables and on all that, but it's not nice. I would not recommend trying this. If you want to do weighted shortest path in Cypher, it is a shorter query, but remarkably, actually, it has a very different structure. Now, it contains a call to a library that you have to install. So there is this GDS library with graph algorithms that you can add to Cypher. And then there is just a hard-coded shortest path algorithm that you have to call with a number of parameters. So this is a bit confusing, in my opinion, because for unweighted shortest path, you can use pattern matching and the normal kind of Cypher ASCII art syntax. But for weighted shortest path, you certainly have to call out to a stored procedure to a library. Okay, so now I focused on Cypher and on Neo4j therefore, but there are quite a few graph data management systems out there. I've put them in this sheet. It's not an exhaustive list, but what is interesting to note is that all these different systems have a different query language. So there is no standard query language for graph systems, regrettably. If you want to know more about the state of the art in these graph query languages, I would wholeheartedly recommend you to read the ACM Computing Survey paper from 2017, written by Renzo and Gless et al. On the foundations of modern query languages for graph databases. And if you just want to consume a presentation, and you may later download this presentation and click on the link, because I have a very extensive survey of property graph query languages as well available, which is a year old. So now that we have kind of a basic understanding of the functionality of graph data systems, let's take them for a ride, for a test ride. And so my colleague Gabor Tsanias organized a very simple benchmark that takes graph data management systems to their home terrain, which is basic pattern matching. This mini benchmark is called, it works on the LDBC dataset, but it is simpler than the full LDBC benchmarks. It's called LSQB. So it's a subgraph query benchmark, and it consists of 9 queries, 6 of which are truly, well, basic pattern matching, and 3 of them are called complex, although they're not really very complex. They just add some optional connections and some negation. Well, okay, so what's to be said about this here is that yeah, also due to licensing restrictions, I cannot sometimes name performance results of commercial graph data management systems due to the VID clauses. But there is actually a Docker container that allows you to rerun these experiments and experience this all yourself. So Google it, check it out, and see what happens. So what roughly happens is actually that all the graph database management systems that we tested did not complete this benchmark on even the medium size. So they were at least an order of magnitude slower than the 2 most competent systems here, which are both developed at the TU Munich, namely Umbra and Hyper. So this is, yeah, what can we say about a result like that? So I say that this points to my thesis that graph database management systems often are still not competent. And competent, I then define as 3 main dimensions: providing performance, providing scalability, and providing reliability. Regarding performance, we have seen, or we see when you try to run this, very, very slow loading speeds, some systems even failing to load at all this data LDBC data set. Yeah, we already saw query speeds that are, well, 30 times slower than the better relational systems. Regarding scalability, some systems actually work, but they only work on very small sizes. So this data size has to be really, really much smaller than the RAM size. We also see very many idle cores, so very little benefit from parallelism during these queries. They don't take advantage of multiple cores, multiple machines, and also not of SIMD instructions. And regarding reliability, which is also very important for users, yeah, that's still lacking. I mentioned the loads that do not terminate, but also queries when they fail to run, they may crash systems, they may come back with errors. And we also found a number of bugs when running this benchmark on various systems. So, okay, that is maybe sobering. Then as to a theory on why this could be the case, I follow Mike Stonebreaker in pointing out certain things that are maybe not optimal. I call them in his style blunders. So I will take you through 6 blunders in graph data systems architecture. So first, triple fallacy number 1, locality lost. So this is definitely applicable to RDF systems, but it's also applicable to schema-free property graph systems that do not want to know what the schema of their vertices and edges is, and that throw basically all their vertices and edges in one big basket. So like one big collection of vertices and one big collection of edges, no matter the structure. And this is then you're basically back at triples, and when you do that, well, you could say, well, I'm smart, and there was a system called Hexastore, and people, and this is actually a common technique. They say, well, if you have just triples, there are 6 different orders in which you could order these 3 columns that the triple is, and you can make a clustered index on all of them, and I have always indexed access, and I'm always good, you know. So because I always have an index. This is, however, not true, because it's not only about having an index. An index is not a good idea in a database system if you have random access, if you have massive random access coming out of that index. And that's exactly what's going to happen. You may actually have some locality, because this query that I have here, I have actually a book query that asks for books from 1996. It could be that your triples from 1996 are close to each other in the first index, but then you're joined to the second index and you join to a third index. This query has 3 triples, so you have 2 joins between them. And both these 2 joins will lead you into massive random access and therefore not good performance. If you compare this with systems where you do have insight into the structure of your data, you know that you have books, for instance, then you could create a clustered index, maybe on year. You could create maybe a partition table. This is the stable of data lakes, actually, partition tables. Or you could actually do nothing, but get this partitioning for free, because very often we have time correlation. And then if you have a min-max index, like in a format like Parquet or Org, you will have min-max index, which are the same as zone maps, which will pick up on the fact that your data is actually time clustered and will provide you this locality. And that means that this query in a system that is aware of structure, in the first place, not a join, but it's actually a scan that will only read relevant data. And this this locality you will lose if you take no interest in structure. And that is triple fallacy number 1. Triple fallacy number 2 is the join jungle. So by denying the structure in triple systems, you will actually create 1 join for every triple in your basic pattern. And these joins, these resulting from star patterns, they are unnecessary, because in a structured system you would not have a join there, you would just have a scan. And there is 2 reasons why this is bad. So reason 1 is that join is one of the more costly execution operators in a database system. So more joins is not good. The second reason why this is bad is that query optimization complexity is exponential in the number of joins. So if you are significantly increasing the number of joins in your query, this query becomes exponentially harder to optimize. And you also see the optimization time in Virtuoso with the number of triple patterns dramatically increase. And you say, hey, but it's flattening off at the end, huh? But no, what's happening there is that the optimizer is bailing out. So it's stopping to search the search space, because otherwise query optimization would take too long. So the end result is that the query optimizer cannot cover the optimization space as well as in a system that takes an interest in the structure of your data. So this is definitely a fallacy and to be avoided. And it's compounded by the third fallacy of triples, the true triple fallacy, which is the cardinality crisis. Because it is actually very hard to optimize these joins. And that is because these joins are not real joins, they are correlated, there are structural correlations. So how to understand this? Well, if I already have the triples that correspond to ISBN number, then the vertices that this is about are books, because only books really have ISBN numbers. Okay, so then it's almost a certainty that there's also an author triple and a year triple. But a query optimizer would make the independence assumption actually get very, very bad query cardinality intermediate result estimates. And therefore, so the two things combined, you have a way, way, way bigger query optimization space, and you have very bad estimates, and that results in performance disaster. The fourth blunder in graph data systems architecture is what I call the graph uniqueness syndrome. And you also see that when you read many graph research papers. So it is like, because you put the word graph in front of your problem, people think that they are in an entirely new domain and everything is greenfield and nothing should be learned. And well, this is maybe true for paper sometimes, but it's also true for systems, that people who design these systems sometimes do think that they shouldn't take lessons from data systems that have been created in the past. An example is, and that's also one of the crucial rallying points of graph data systems, is the importance of using pointers, because an edge is like a pointer, and therefore I also want to use a memory pointer, and I want to follow, I will do navigation in O1, and an equivalent of that is putting stuff in arrays and using offsets and, and following an offset. But this comes at a cost. So if you have stuff in an array, how do you do updates? Or if you follow pointers between objects, what about memory locality? You have 1 billion objects. Are they really close to each other? Can you do a fast scan through 1 billion Java objects? Probably not. And are you really avoiding doing joins, or are you just calling joins something else if you do navigation like this? So my point of view, and that's of course reflected in the title, is that graph database management systems should build on all techniques that we already know. And this is because if you look at the functionality of graph query languages, we want that relational operators. So you want to scan data, you want to filter data, you want to have a group by, you want even sometimes to join on value as well. So actually a graph data management system should be a superset of what a relational system already is. And that means that we need to look at techniques and their properties that we know very well and improve and build on those. So like buffer managers, transactions, a query algebra, statistics, and optimizer. And then only when you have those, and then you add graph specific functionality. So the fifth blunder, a pitfall, sorry for the lame pun here, key value APIs. So one of the misconceptions I have seen is the belief that APIs are faster than a query language. So we shouldn't maybe even support a query language. Well, actually, this is not really true, because almost all systems I know are now introducing some kind of graph query language. But actually, the idea of using an API, and then the API that's commonly used is one where you just follow pointers, you follow edges, is a very dangerous concept, because this is a very fine-grained. So think about navigating a social network. If you do 3 steps, you already are at 1 million people. And if for every vertex that you read, you do an API call, that query that does just 3 steps will have to do 1 million API calls. And the telltale sign of a system that has this wrong level of abstraction of the API, I think, is when systems advertise as being pluggable and being able to run on top of various key value stores. These key value stores just have this get and put API. So you know that you will be in 1 million API call hell, when performance hell, when a query of any significant size, well, 3 steps, like is executing on a system like that, it cannot perform. So if you want to design an imperative API for your graph system, make it a bulk one. So where a single command actually does a whole 1 million iterations. I did mention the word query algebra in the previous slide, because then you basically have a query algebra if that is your API, your imperative API. And the 6th and last blunder of graph database design is what I call booby-trapped query languages. Now it is very tempting to create a query language that has very rich functionality and offer it to a user. But if that rich functionality means that it's not tractable to compute queries in general, and if you are addressing that problem by having a query optimizer find those queries that are tractable and then execute those with a good algorithm, it actually puts your users in a booby-trapped world where they will type queries that sometimes work, but then when they make one small mistake, suddenly the query isn't tractable anymore and the system basically hangs, given error, crashes. Is that a good user experience? No. You should avoid such query languages, therefore. You should only have query languages that allow to express tractable queries. So in the case of graph query languages, you could think about, well, using explicit syntax for reachability and weighted shortest path. So the wrong approach here is actually the SQL approach, where you have the general concept of recursive queries. These recursive queries are typically not tractable. Only special cases are tractable. You could make a very, very special optimizer rule that will look at very, very complex SQL, deduce that this is a Dijkstra algorithm, and then use a Dijkstra algorithm or a Bellman-Ford algorithm. But you should not even contemplate doing so. You don't want to be in that space. You should make a query functionality that always leads and reliably leads to a tractable query execution. A second example are path expressions. So I mentioned the cleany star, like nose star in my example queries, but you can, rather than doing a cleany star on a single edge or nose, you can also actually match a pattern, and then you get regular path expressions, and then do a star of that regular pattern. So you can actually do quite advanced pathfinding. But this also very quickly can get you into tractability hot water. There is a class of path expressions called regular expressions with memory, called REMs, that was identified in Oracle's PGQL and also used in GCore and used, I think, in SQL PGQ, which has the nice property that it is always mappable to a tractable problem. So this is the kind of thinking and the kind of language design that we want, allowing to have maximal expressivity, but always within the realm of tractability. So now we are progressing quite a bit. Let me give you a blueprint of what I think a competent graph database management systems architecture looks like. So we would start from a competent base. And in this case, I will assume a bit of focus on analytics, because if we do a lot of pattern matching and pathfinding, this is a system that's supposed to be good for analyzing graphs. And then I would definitely start with columnar storage and lightweight compression. And the reason why is simply that you want your data to be compactly represented. And if you do this, your data is like the compression, and the columnar compression specifically gives you a factor 3 or 4 on average of compression. So that means that you can store 3 or 4 times more data in your memory or on your SSD, which is very good. Then you would pair this with a fast query executor. So something that executes some kind of algebra efficiently. And there are 2 techniques for that. One is just-in-time query compilation, a technique that has been demonstrated to work very well in the systems Hyper and Umbra of TU Munich, and also other systems as well by now. On the one hand, so maybe base yourself on Umbra. Regrettably, Umbra is not open source. If you send a nice mail to the TU Munich, they may give you a binary, or you go for a vectorized executor. So at CWI, we are building an embeddable analytics database called DuckDB that is open source and that you can easily build on. And it has very good query execution performance. You would definitely go for a buffer manager, because you will not want your system to be restricted only by main memory. Specifically, there is this line of work on lean store, where the idea is that we will be able to execute as if on almost RAM speeds on flash memory, on flash drives. And there is a lot of flash has very low latency nowadays, very high bandwidth. And you would do that via a buffer manager. You need a buffer manager, and you also need control over your memory. So that concretely means that you should not write a system in the JVM, because then you lose control over memory. So it means that you implement this system in C++, C, or maybe Rust. And regarding query optimization, you would use a bottom-up dynamic programming query optimizer, which is the state of the art. And you would pair that with state of the art statistics provided by samples and hyperlog logs. And you would also want to be able to profit from many cores. So you would implement Morsel-driven parallelism, where you have shared hash tables, where you can have low latency and low contention multi-threading using atomics and fine-grained load balancing, so that all the cores are busy and you have good parallelization. All these principles, by the way, are adopted by both DuckDB and Umbra. DuckDB being the vectorized engine and Umbra being the JIT engine. Okay, going from there, you want your system to be aware of what the storage structure is. So what kind of properties, so how is your graph shaped? Don't put them all in a single basket, one with vertices and one with edges, or don't do that, because then we get into triple fallacy territory. We want to avoid that. So the GDBS must know about the structure. So it must know about the labels or the entities of vertices and edges, and know about the common columns that they have as properties. So the properties in the property graph model will become columns in the tables where you store your entities. So you can either do that by just enforcing an explicit schema. There are very many use cases in which this is not such a big problem. And then you could also build on the work of the LDBC property graph schema working group, or you would not assume a fixed schema, but you could be smart. There is interesting work. For instance, there is this work now, JSON tiles, that was in Sigmod 2021. In the context of JSON, but JSON also doesn't have a fixed schema. And this is, what's being done is that when you load JSON, you automatically detect the structure of this JSON, and the structure of JSON is very often very repetitive and very similar, and actually store this in columns. So, and this is also a feature that is one of the most popular features in the Snowflake SaaS database system. I also put a second reference to a paper of ourselves with quite advanced techniques of deriving or learning about the structure of untyped or data without schema, specifically there in the case of RDF. So this is a way around potentially not having structure and still having it, and therefore having good efficiency. Then the thing about fast navigation. So is it really that important or that crucial to have O1 navigation to be able to follow a pointer? Or can we actually also have it in a system like this with a buffer manager? So one idea is that you consider this to be so joins that you would do in graph navigation. You could have special optimizations for these that would trigger if a hash join would see that the key in the hash join is in fact from a very dense domain, because these vertex identifiers could be from a dense domain. If they would be offsets, then you actually wouldn't have to hash. You can just put your data in an array, and you can actually have the same performance as you have in a native system. Or at CWI, we had work on TCO, which is in the area of packed memory arrays, where you do have data stored in arrays, and therefore you do have data that is positionally addressable, but is still updatable, because that is the problem if you put things in a fixed array, that you cannot really update this data very easily. So I would like to point you to this PVLDB 2021 paper about the TCO, and also to the paper in CIDR 2022 on GrainDB that uses DuckDB and adds some support for positional joins in order to accelerate graph workload. So that's definitely the direction that you could be following if you want to optimize joins further. Okay, then we get into very graph-specific territory, because we would want to have path-finding algorithms. Algorithms to find paths in a graph, to find shortest paths specifically, because finding all paths is intractable, as we know, but also to find weighted shortest path, for instance. Theoretically, these, by the way, are also intractable because you can have an unlimited amount of shortest path if all the paths have the same length. But in practice, this is not very relevant distinction. But what is important if you add a pathfinding algorithm like Dijkstra or Bellman-Ford is that it is a bulk algorithm. Because in these graph query languages, they will do this pathfinding between typically two variables that are in such a pattern matched block. And so the general case will be that you have many bindings for the source pattern and many bindings for the destination pattern. So it's somewhere in the middle between finding a single path and the all pair shortest path problem. But your algorithm needs to be able to handle the whole spectrum of those effectively if you want to have this in a system. You should not implement a single path finding algorithm between a single source and destination and invoke it a million times probably. That's not going to be a good idea. What's also a good idea is exploit the fact that you're not finding one path but many paths, or bulk path finding, with specific algorithmic innovations. One of them is landmarks. I pointed here to a SIGMOD 2013 paper about using landmarks in order to prune quickly shortest path searching. It would be cool to see something like this adopted in a graph database management system to accelerate pathfinding operations. I also point to BTW 2017 that shows pathfinding algorithms that play into SIMD instructions, and I can actually do many path findings at the same time in different lanes of SIMD registers. Finally, the complexity of subgraph matching. So subgraph isomorphism, so checking whether two subgraphs are isomorphic, is in MP, and it's actually a still active area of theoretical computer science research. But we know that for graphs of bounded degree, the complexity is polynomial. And still, if we look at a triangle query here, so we have a triangle between two persons and a tag, it has been proven that addressing this using binary joins, and with binary joins, I mean joins between two tables, which is the normal way that database systems resolve joins, is provably suboptimal, because that would be the complexity of that would be in the order of the square of the amount of edges. Whereas for triangles, it is proven that there can be only maximally the amount of edges to the power 1.5 results. That is the worst case outcome of, therefore, any triangle query. And there are algorithms that can guarantee that they will not spend more effort than this bound. These algorithms are called worst case optimal joins. And it has been an active area of research in the past 15 years, obviously starting in the theory community, although concurrently this idea was actually implemented in a system called logic blocks, and there was also a paper from logic blocks about a leapfrog tree join. These algorithms that have been proposed were originally trie-based, so they require you, well, they actually are multi-joins, so all the patterns, all the edges in a pattern are executed potentially at the same time. It is necessary to sort and materialize all the relations before to do so, and to build a tri-data structure. What's interesting is also a question: when do you decide to deploy such a join? So this question is addressed by the PVLDB 2019 paper cited here. And also the question is if sorting and building a trie is really execution-wise the smartest or the fastest thing to do. And a very interesting paper from 2020 from TU Munich described for the first time a hash-based worst-case optimal join that is also integrated in Umbra. So Umbra is currently, of the systems that we tested, the only one that is deploying worst-case optimal joins, or multi-joins that can resolve a complete pattern in one go, and thereby avoid the problem of very large intermediate results, because that's the problem that binary joins face. That if you create this triangle, for instance, you have first edge square intermediate results, and then when you close the triangle after 2 steps, and then when you close the triangle, many of those results turn out not to be relevant. So avoiding these intermediate results is what these worst case optimal joins are good for, and therefore you should include them in your system. So in current industrial system, we know that there are implementations in the product of Relational AI, which is a young graph data management company. Well, Logic Blocks, I already mentioned this. There's an open source system called XTDB, which also has this, and not sure about the speed of that system. It's implemented in Clojure. In the academics, there's Umbra, I mentioned that, and also at CWI we developed something for Spark called Edge Frames, where you can do worst case optimal joins in Spark queries. So this leads me to the last slide of a competent architecture, because there are many things that have not necessarily been decided or have been are not where the optimal solution or a good solution is not necessarily known. So this is also where, well, you could possibly do research. So you could, for instance, work on this smart schema discovering loading for property graphs. That would be an interesting direction to work in. You could work on property graph schema languages like the LDBC working group does. We at CWI are very interested in efficient worst case optimal joins, and specifically we would like to have a vectorizable worst case optimal join, because the hash based one that Umbra uses is suited for their JIT code generation approach, which goes more like tuple at a time. I already mentioned the problem of doing efficient cheapest path and shortest path algorithms that exploit the fact that we do these in bulk. There is a general question, and when you integrate graph query processing with other query processing, you find many query optimization challenges, and so optimizers will have to be improved in order to deal with this properly. And an open issue is transactional semantics for graph data. For this, I also point to a TPC-TC paper by Gabor Zarnias and myself and others that was published in 2020. And for a general overview of a panoramic view of open problems in graph data processing, I would like to point to the excellent tutorial and also keynote that Tamer Osu gave 2 years ago in BLDB. Okay, we're almost there. I promised that I would talk shortly about this upcoming extension of the SQL standard called SQL PGQ. So what's that? So here you see a snippet of what is being proposed. So what it does is you start by declaring or creating a property graph where you point to data that is already stored in tables. So create property graph statement identifies a vertex table or multiple vertex tables. So in this case, there would be a table having customers and there would be a table having accounts. And the columns of these tables could become properties of these vertices. And also similar for edges. So you would have the owns account and the transfers between accounts relationships, edge relationships, and their properties that you declare in this way. And you also describe in this statement how these vertexes join to the edges. So that's a primary and foreign key relationship, essentially. And then after you define such a property graph view on your relational data, then there is a SQL extension where you can do these ASCII art style match statements. So they are arguably shorter and easier to type and maybe read than SQL statements that do exactly the same thing. But these you could also translate, of course, into joins as I demonstrated, although it would be longer. But there would also be functionality for shortest paths, cheapest paths, so both the length of a shortest path, the cost of a cheapest path, and actually also retrieving what is a cheapest or a shortest path. And finally, after doing this property graph query, you get back a table, and this table is wrapped as a graph table and comes back as a nested subquery in the SQL result. So then you can also join this property graph query result with other relational tables or with other property graph queries if you wish. So we think that it's definitely better than SQL XML, which is the horror of horrors, where you would have all of this in a string. But no, here actually this is properly in the SQL parser, and names and variables are are properly recognized. So it's not as bad as it could have been. And it will add some interesting functionality, and it actually will bring relational and graph systems very close together. So it's also time for graph systems to become more competent, because they will get likely some competent competition. Yeah. So one of the disadvantages of ISO standards is that the specs are not freely accessible. However, we have a loophole for you for that, because as I mentioned, this property graph business and the development of these languages was also coming from an initiative from LDBC, and LDBC has a liaison agreement with ISO. So all LDBC members can have access to these specification documents of SQL PGQ. And it's actually free to become an associate member for LDBC. So go to the LDBC website, become an associate member, and then you can also look at these documents. Finally, there is in this ISO group also talk of what we call a proper native graph query language. That's called GQL. More information on that is in the website gqlstandards.org. We do expect this query language will allow not only to give back tables, to return tables, but to actually also construct graphs as a result of a query. But we do not know. I mean, we don't know when this will be approved and when it will be finalized. But this is definitely also an ongoing project still, and it's similarly also associated with LDBC in ISO in the same working group. And I include some pointers for that. So with that, I'm at the end. It's time to wrap up. It's time to conclude. I discussed the relationship between graph data management systems and relational data management systems. I've walked you to pointed you to some use cases, and I do anticipate that the use of graph systems will continue to expand. I talked quite a bit about LDBC. It has created useful benchmark, but it also has gotten involved into query and schema languages. Here, I want to mention that in Philadelphia at SIGMOD 2022, on the Friday, there will be an open technical user community meeting that you can also attend. It's one of the workshops essentially it's like a workshop in SIGMOD, where we hopefully will physically come together then. And yeah, I did conclude that, or I pass you my opinion that the current generation of graph data management system is often not competent yet, and discussed some pitfalls that may have led to that. I outlined SQL PGQ and also the blueprint of a competent graph data management system. And CWI is also building a PGQ extension module for DuckDB that will turn it into such a system. And hereby, I would also like to thank, first of all, Gabor Sarnias, who is also co-leading LDBC, in fact, and made possible this nice presentation. And I would like to thank Hannes, Mul Eisen, and Mark Raasveld for creating DuckDB and making it available, creating DuckDB, but also DuckDB Labs, which is a spin-off, and the DuckDB Open Source Foundation, founding that and making it available for the community. And with that, I am really done and ready for questions.
Yeah, thanks a lot, Peter.